In this video, we're going to talk about how we can graph polynomial functions. We would like to graph any polynomial function, and so we're going to talk about the methods that we could use to help us do that. Some of the properties that we want to know about polynomial functions, and this is going to be something that's true of every polynomial function, is that the graph of polynomial functions are smooth, they're continuous, and they're smooth and continuous over the real number line. So their domains are from negative infinity to positive infinity. All right, and I'll draw a sample or an example of a polynomial function. For instance, I may have a function that looks like that. That will be typical of a graph of a polynomial function. Notice there's no corners or cusp or anything like that. It's just a smooth function. A linear function is also a polynomial function. We also call that smooth. And basically, these functions are continuous over the real number line, meaning once I start to graph this function, I can graph the entire function without picking up my pencil. And that's from negative infinity to positive infinity, no matter what type of polynomial function we have. And so these functions have good properties that you will learn about in calculus. But for now, we just know that they're smooth, continuous, and they have a domain that's all real numbers. Our goal is to be able to graph these. And so what we're going to do is we're going to learn some of the properties of polynomial functions so that when we look at the actual algebraic expression that that function represents, we'll be able to figure out some of the properties of the function. One thing about power functions is that their leading term, remember we have that long expression for a polynomial function, but power functions that are polynomial functions, they're kind of controlled. Their overall behavior, or part of their overall behavior, is controlled by that leading term. And that leading term is that term with your the degree of your polynomial. So a sub n times x to the n. When n is a positive whole number, positive whole number, then we call a function that just has that form a power function. For instance, a function f of x equals negative 3x squared, it is called a power function. Now, regular polynomial functions may have some extra pieces. I'm going to do this in a different color. So that's not considered a power function, but this leading coefficient itself, this leading term itself, would be considered a power function. Another example of a power function that is a polynomial is something like 5x cubed, right? That's another power function. One of the things about power functions is that power functions sort of behave exactly the same, right? So when you look at their graphs, and we're going to look at power functions, I have power functions graphed here that have a leading coefficient of 1. So that a sub n is a 1. So I have x squared here in that blue, x to the 4th in the pink, x to the 6th in the green here. So the coefficient is 1, and each of these have an even degree. 2, 4, and 6 is the exponent. They all look like parabolas. The difference is the higher the power, the quicker the function increases, and the flatter that function is as you get closer and closer to x equals 0. So as you get closer and closer to x equals 0, it's flat, but the further you go, the quicker it goes up, right? But generally, they look like f of x equals x squared. When I talk about polynomial or power functions of odd degree, like x to the 3rd, x to the 5th, x to the 7th, I have x to the 3rd here in blue. I hope you really can see that. I have x to the 5th in pink and x to the 7th in green. It may be hard to see. But it's kind of the same thing. They generally have the same shape as f of x equals x cubed. They approach 0, or they're flatter near the origin, but as you increase the exponent, they grow quicker and quicker, right? Now, these power functions basically follow the shape of y equals x squared, and they follow the shape y equals x cubed. So x squared and x cubed kind of guides the shape of the even and odd degree power functions. Well, it just so happens that one part of the function that we're going to be interested in is what we call end behavior, right? So what it says is polynomial functions behave similarly to power functions of the same degree at extreme values of the domain. they have the same end behavior. All right. And so what this means, and it kind of makes sense if you think about it, as when I'm talking about this extreme ends of the graph, I'm talking about like this part of my graph and this part of my graph here, right? That's as x approaches infinity, and on the left side of my graph, that's as x approaches negative infinity. That's what I mean by the extreme ends. No matter what your polynomial, what even degree polynomial you have, it is going to have the same end behavior, or it's going to continue to go up, up, up on the left side of your graph, up, up, up on the right side of the graph, just like f of x equals x squared does in this graph. The same thing happens with f of x equals x cubed. As x approaches infinity, which is to the right side of your graph, and as x approaches negative infinity, which is the left side of your graph, your y values are basically doing the exact same things. That's what we mean by end behavior. And so not only does it happen for power functions, but it happens for polynomial functions. If you think of a polynomial, now I wrote these, okay, I'm going to add some stuff here. So say we had these two polynomial functions. That's the one polynomial function, and this is another polynomial function, right? Well, as x approaches infinity and negative infinity, the term that's in these expressions that's going to have the most of the power is going to be this negative 3x squared, right? Because if I square infinity, that's going to be way, way, way bigger. Or if I square a big number, it's just going to be much, much bigger than just having that number to the first power or subtracting 7, right? So I'll add infinity and negative infinity, which is on the extreme ends of your graph, on the right and the left of your graph. These two terms are not going to matter in my squaring function. And then I meant to put a squared here. These three terms are not going to matter much if I look at this type of function. Only the term with the highest exponent is going to kind of be dominant and control the behavior of the function. That is what we mean by end behavior. And so end behavior is a description of what f of x does as x approaches. So we say x, and then this arrow to the right means approaches. I'm going to put negative infinity, and then x approaches positive infinity. And I'm seeing up here where this should have been a positive infinity because that's the right side of the graph. So I apologize for that. All right. And so since that leading term is going to have all the control, then we know how our graph, we know how to figure out our end behavior of our graph by looking at the degree of the polynomial, but we also have to look at the leading coefficient, which leads us to what we call the leading coefficient test. It says let f of x be a polynomial function, then the end behavior of f can be determined by the degree of f, that's the degree of the exponent of the polynomial, and the leading coefficient. The leading coefficient is that a sub n, right? That number that's multiplied by your variable of highest exponent, right? So let's talk about when our polynomial has an odd degree, right? When our leading coefficient is greater than 0, that means positive. Our end behavior is going to look very similar to our parent function, which is f of x equals x cubed. The graph of that function, oh Lord, that's a bad graph. I'm so sorry. All right, it looks something like that. I'm going to try to draw a better graph. All right, it looks something like that, right? And so the end behavior of this function is going to be as x approaches negative infinity, f of x, when negative infinity for my x values are on my left side of my graph. And so what I'm going to fill this blank with is what my functional values or my y value of my function, my y values of my function is doing as I approach the graph to the left. Well, to the left, my graph is going to continue to go down, down, down to negative infinity. So the end behavior of this function is negative infinity. As x approaches positive infinity, infinity on my x-axis is here. If I trace my graph, it's going to continue to go up, up, up. So going up, up, up on my y-axis is positive infinity. So I'm just going to use infinity. So every polynomial of odd degree with a positive leading coefficient is going to have this end behavior here, right? If the leading coefficient for that odd degree polynomial is going to be negative, Well, all we have to do is think about what happens to the opposite or the negative of our cubing function. That just reflects this about the x-axis from our knowledge of our transformations of functions. And we'll see that we get a graph that looks something like that. And so as x approaches negative infinity, our function continues to go up, up, up to positive infinity. The y values are getting larger and larger. And as x approaches positive infinity, that's the right side of my graph, my function is going down, down, down. That's negative infinity. And so knowing x cubed and then negative x cubed, knowing those graphs will help you determine your end behavior polynomials of odd degree. Now, as I go to polynomials of even degree, we have a power function, f of x equals x squared, that has a positive leading coefficient or coefficient, and f of x equals negative x squared, that has a negative, right? So this is our parabola function. It looks like that when it's positive. Remember, negative infinity on x is here, positive infinity on x is here. So as x approaches negative infinity, that's the left side of my graph, my function continues to go up. So we have f of x approaches infinity. And then on the right side of my graph, as x approaches positive infinity, our functional values are getting larger and larger. So we also have positive infinity. We reflect that about the x-axis, and we get f of x equals negative x squared, and my graph approaches negative infinity in both of these instances. All right? And so now we have the end behavior. I don't want you to memorize these lines here. You don't have to memorize these lines. All you have to do is use your graphs of f of x equals x squared, x cubed, negative x cubed in order to help you figure out what your end behavior would be, right? And so it says for each function, determine the behavior of the function as x approaches negative infinity and as x approaches positive infinity. Let's look at B together, and I'm going to allow you to do this one on your own, okay? And so here I have g of x equals x minus x cubed. Well, I'm going to write this polynomial so that my first term has the highest exponent. So I'm going to have a minus x cubed plus x. And remember, with the leading coefficient test, we look at the leading coefficient only, because at positive and negative infinity, it is the only thing that's going to guide the behavior of the function, right? And remember, it's going to behave like f of x equals negative x cubed. We already know that that graph looks like this. And so we know that as x approaches negative infinity, our y values go up. So we're going to say as x approaches negative infinity, f of x approaches positive infinity. You don't have to put the plus sign there. And as x approaches infinity, positive infinity, which is this side of our graph, our y values continue to go down. We can say f of x approaches negative infinity. This, my friends, is your end behavior of your function. Not only do we, so that's the end behavior of the function, right? So by knowing this power function stuff led us to knowing that a polynomial, the leading term is going to be the dominant feature as x approaches a positive and negative infinity. That's the end behavior of your function. Now we want to graph a whole polynomial, and so what we're going to need to do is we need to know what's happening in the middle of a function. And so one of the things that we could find is the real zeros of your polynomial functions. We already found that your zeros of a polynomial, regular zeros, are the values of x that make your polynomial function equal 0, right? And so the real zeros are those real numbers that actually make your polynomial equal 0. Remember, we said that when they're complex, we can't graph them, so those won't show up on your graph. So your real zeros of your polynomial are where your polynomial function equals 0. They're the exact same thing as your x-intercepts. So this polynomial here has 4 real zeros, and it's the solution to the equation p of x equals 0. Well, it's going to be a fact here, and I'm going to draw this graph slightly different, that sometimes when we have these x-intercepts or these real zeros, that sometimes our graph cuts through our x-axis at that 0, and at other times it touches and turns around and goes back up, so it doesn't cut through, but it just touches your x-axis at that 0. And knowing that information could help us graph your polynomial functions. And the way we determine that is to look at the multiplicity of a real 0, all right? The multiplicity of your zeros is the number of times a zero's associated factor appears in a polynomial. All right, it's associated factor. All right, so whenever we solve polynomial equations, right, we know that we should get n zeros. Our fundamental theorem of algebra told us that we should get at least 1 0 in the real number system, right? That's not the real number system. That's a member of an element of the complex number system, right? And I told you in a previous video that when you have polynomial functions, you're actually going to be able to find n zeros, right? So polynomials have n zeros. The multiplicity of the zeros is going to be coming from their associated factor, all right? Now, these zeros are not necessarily distinct. For instance, if I have a polynomial that's this polynomial right here, we know that this is our cubing function. It's shifted to the right 1 unit, and so we will be able to graph that polynomial function. But if I want to find the zeros of this polynomial, then I would have to set this equal to 0 and solve for x. For me to solve for x, I take the cube root. I get x minus 1 equals 0. And there we have it, x equals 1. That is my solution. Now, x equals 1 appears to be only 1 0 of that polynomial function. And that's the only solution to that equation. There are no others. There are none in the complex number system. That is the only solution. And so when I say that the polynomials have n zeros, well, it makes it appear that this is not true, especially for this example here. And I'm going to submit to you that it is. All right, this 0, x equals 1, actually appears 3 times because this is x minus 1 cubed, right? We started with x minus 1 cubed. We took the cube root to get rid of that cube so we can solve this equation and find that that was x equals 1. But this is x minus 1 times x minus 1 times x minus 1, right? That's x minus 1 cubed. And so when we solve this equation, we actually get x equals 1 as my solution one time. We get x equals 1 as my solution another time. We get x equals 1 as our solution another time when we set each of those equal to 0. We don't write that out in practice because it's definitely quicker to do this. And so looking at the associated factor, which is x minus 1, that's what we're calling our associated factor. That is what I'm talking about here when I speak of multiplicity. It's the number of times a zero's associated factor appears in a polynomial. This associated factor appeared 3 times, so x equals 1 has a multiplicity of 3. It's one single zero of that polynomial, but it's actually 3. All right, I know it's one number, but it's 3. It appears 3 times. Okay. By knowing the multiplicity, we can determine the behavior of the function at each 0. It's going to tell us whether our graph is going to cross the x-axis or just touch the x-axis at that 0. And just as we've had the parent functions before, these parent functions here, f of x equals x squared once again, is our parent function here, and f of x equals x cubed is our parent function here. It's going to tell us about the multiplicity of our 0. If I were to try to find this 0 of this polynomial function here, I would have to take x squared and set it equal to 0. I take the square root of both sides and I get x equals 0. This one has a multiplicity because it came from this associated factor, which has an exponent of 2, so the multiplicity of that is 2. If I wanted to find the 0 of f of x equals x cubed, I take x cubed. That's the associated factor, because if I take the cube root of both sides, I get x equals 0. This is the thing that allowed me to see that x equals 0 was my solution. That has the multiplicity. Well, take the exponent of that factor, and the exponent of that is 3. And so that has a multiplicity of 2. This has a multiplicity of 3. This multiplicity is even because 2 is an even number. This multiplicity is odd because 3 is an odd number. What does the graph do at f of x equals x squared at its only 0? It touches and turns around, right? So when there's an even multiplicity, the graph touches the x-axis but doesn't cross it at that 0. And then when my multiplicity is odd, the graph crosses the x-axis at that 0, all right? And so let's look at an example where we look at this. Let's look at example B here. I'll allow you to do example A on your own. I want to find each zero, find all zeros, their multiplicity, and we're going to determine the behavior of the function at each real zero, okay? And so if I want to find the zero of this polynomial function, I'm going to replace f of x with 0. That's like saying y equals 0 and solve for x, which is the same process we would use to find the x-intercepts because real zeros are x-intercepts. All right, I factor out a x squared. And what I'm going to do here, there are two ways that I can do this. I'm actually not going to factor any further. All right, you can factor further. All right, I'll come back and show you that possibly. But I have a product of two things and they equal 0, right? So I can set both of them equal to 0 and I can solve for x. Okay? So if I take the square root of both sides, I get x equals 0. All right? It's pretty clear that this x equals 0 comes from this x squared, which has a power of 2, right? So the multiplicity here is 2. And that means my graph touches my x-axis, but doesn't cross. I'm just going to say touches. When I solve this equation here, this comes from x squared minus 1, which is to the first power. I don't want this to be confusing. Now, if I solve this equation this way, I'm going to add 1 to both sides, and I'm going to take the square root of both sides. All right? When I take the square root of both sides, this becomes x equals plus or minus 1. Okay, plus or minus 1. This came from a square, right? This came from this thing to the first power, right? But the multiplicity is actually 1 here because I got 2 solutions from here. What we could have done here is done x squared equals x plus 1 times x minus 1, right? And so the multiplicity of the x equals negative 1 is 1, and the multiplicity of x equals 1 is going to also be 1 here. All right. Now, there may be times where your multiplicity may be bigger than this number, right? If you didn't factor completely, right? But since I have a square here, I know that this factor has a power 2, so I should get 2 solutions. Had I only gotten 1 number out of this, then it would have been a multiplicity of 2. But since I got 2 numbers out of this squared thing, the squared polynomial here, and my multiplicity of each of those are separated, and they're both 1, right? So I get x equals negative 1. It has a multiplicity of 1. So my graph crosses. And then x equals positive 1 has a multiplicity of 1, and my graph crosses. All right, the point that I'm trying to make here is that if, let's say I had x cubed minus 1 equals 0, right, which was right here, then I get x cubed equals 1. I take the cube root of both sides, and I only get x equals 1. In this case, since I had x cubed minus 1, my multiplicity would actually be 3, all right? This was 2 because I separated it into 2 separate. I had to use that plus or minus, which gave me 2 separate numbers, right? So that split this exponent x squared minus 1 up. Here, if that were x cubed, now I just made this up on the fly here, but if that were the case, then my multiplicity would actually be 3 instead of 1. All right. And actually, we'll study this a bit more, because if you can tell me whether this is correct or not, I'll give you some bonus on your next quiz. Is this correct? Is the multiplicity 3? All right, now that I made this up, now I'm second guessing myself and I actually know the answer to that. But if you can give me the answer to this, I will give you bonus on your next quiz. All right, that's multiplicity. Think about that and then let me know. Bring it to class or something. All right, graphing polynomial functions. All right, graphing polynomial functions. So that's all we're going to do to determine how to graph our polynomial functions. We're going to start by finding the end behavior. We're going to find all of the zeros, their multiplicities, and the behavior near them. We're going to find our intercepts. And in fact, since our real zeros are our intercepts, we're only going to find our y-intercept because we already have our x-intercepts if we find our real zeros. You can do a table of values, but we're going to skip that step, and I'll show you how we can graph without doing a table of values. And then we're going to graph a smooth continuous curve. All right. So we're going to sketch the graph of this function right here, negative x cubed plus 3x plus 2. Right. First thing I'm going to do is I'm going to study the end behavior. And we'll see how we can use that to help us graph, right? Well, when we look at the end behavior, we're going to look at the leading term, which is negative x cubed, right? So remember, negative x cubed, the graph is looking something like that. And so I can say as x approaches negative infinity, f of x approaches, well, our graph goes up to the left, so that's going to be a positive infinity. And as x approaches positive infinity, f of x approaches, well, our graph goes down to the right, so that's going to be a negative infinity, right? And so what I like to do is notate on my graph that on my left side of my graph, since f of x goes positive infinity, I'm going to put an arrow to tell me to continuously go up. And here, since my graph approaches negative infinity, I'm going to put an arrow to tell myself or remind myself that my graph needs to go down, all right? Now I'm going to find my real zeros. All right, to find my real zeros, I set my function equal to 0 and solve for x. Well, we should be able to factor, but this is not a quadratic polynomial, so actually we don't know a method to factor. And so what I'm going to do is I'm going to use synthetic division to help me determine what this would be. All right, and so remember, you have your factors of p over q, your possible rational zeros. So this plus or minus 1 and plus or minus 2 will give you your possible p's, and my possible q's is plus or minus 1. So my possible real zeros are plus or minus 1 and plus or minus 2, right? And so with that, we're going to try some with synthetic division. I've already kind of done some of this work. And so I'm going to try -1. All right. I'm going to fill in my synthetic division chart. So -1, that's 1, 2, right? So I get this right here. So I know that x equals -1 is a real zero, right? Uh-oh, I've gotten to a quadratic equation, right? And so what I could do is say, oh, well, all I need to do is I need to look at this quadratic equation and solve that quadratic equation, right? Now, it's easy to solve quadratic equations, right? Oh, I can factor this, so I divided both sides by a -1 because I don't like when I have a negative leading coefficient. And I find two numbers that multiply to give me -2, but add up to a -1. A -2 and +1 work. So let's set them both equal to 0 to find our other solutions. And so I get x equals 2 and x equals -1. Now notice, when I did my synthetic division, I got x equals -1. And when I did this, I got x equals -1. And I should expect to have how many zeros? My leading coefficient, or my leading term, has an exponent of 3, right? So I suspect 3 zeros. I have 2 of them that are the same. So this has a multiplicity of 2. That means my graph touches my x-axis at that point. And this one has a multiplicity of 1, which means my graph crosses the x-axis at that point. Now we will find our y-intercept. That means you set all of your x variables equal to 0. So I'm going to plug in 0 here, plug in 0 here to cancel, and I'm left with y equals 2. So my y-intercept is the point 0.02. And with that information, I have enough information for me to graph, right? So I'm going to plot my x-intercepts, -1, +2. I know that I'm going to cross my x-axis at 2 and touch my x-axis at -1 because of the multiplicities. And my y-intercept is 2. Now, I say that we don't have to do this step here, this step 4 here, because we know that all polynomials are smooth continuous functions, right? And so what I know is that my function has to end over here, end going up, right? Then it has to go to -1. It's going to touch my x-axis at -1, turn around, and it has to go through this point here, which is my y-intercept. Now, I don't know how far my function is going to go up, right? But I do know that it has to go up to 2, that y-intercept of 2, and come back down and cross the x-axis at 2. And so I'm going to draw a graph that has this behavior. My graph may be a little off. I don't know how far up I need to go, but I know at some point I'm going to have to turn around because I've got to go and get back to this point right here. And I'm going to cut through my x-axis at that point. I'm going to extend my graph, and that is an acceptable graph of our function. Okay? That is an acceptable graph of our function. We need to know some more calculus, or we need to know some calculus, or either plot some more points, that means to create a table of values, to allow us to see how far up this may go, or if it went up between -1 and 0 past y equals 2 to get back to that point, and then went down. We don't know that with the algebra that we have, but this is what we have, and that gives us a pretty good depiction of what this graph would look like. Okay? So that's graphing polynomial functions. Now we're going to look at polynomial inequalities. Now we're back into the one variable case, all right? So there's no two variables here, but we can think of this as like a polynomial function, but we're saying when does the polynomial function, when is it less than 0 or greater than 0 or less than or equal to 0 and greater than or equal to 0. So in this case, we're talking about less than 0, right? We're going to use the test point method, which is the same method that we used when we were talking about quadratic inequalities, right? Where we find the zeros of the polynomial, we plot them on the number line, and we choose test points in between to substitute back into the polynomial function in order to see if we get a value that's greater than or less than 0. And then we'll be able to pick the points, the intervals that match up with the inequality that we have. So this polynomial inequality already has 0 on one side and everything on the other, right? So what we're going to do is we're going to go ahead and set this equal to 0 so that we can find the zeros. The 0 is where it will cross the x-axis, right? And so I'm going to do this by factoring. Now, if you wanted to, you could use your rational zeros theorem, and you can find the zeros using synthetic division and whatnot, right? I'm not going to do that because this is one that can be factored. And if I can factor, then I'm going to factor, all right, because sometimes it's less work. So I factor that in this manner here. I set each of my factors equal to 0. And we solve for x. And so I get 3 zeros, right? Just for fun. The multiplicity of this 0 is 1. The multiplicity of these 2 zeros are both 1. Okay? They're both 1. All right, and so I have my 3 zeros, so I'm going to put them on the number line. Remember, the square root of 2 is approximately 1.4 something. And so I have -2, negative square root of 2, and then I have a positive square root of 2 on my number line. Right? Now, this polynomial inequality here was factored into x plus 2 times x squared minus 2. All right? And so I'm going to use that information to help me choose test points, right? So my test point on this interval is going to be -3, right? I'm going to plug in -3. I can plug it into the original inequality, or I can plug it into this inequality here. If I plug in -3 into this inequality, that's factored, and think a little more in my head, right? So I don't have to do those calculations in my head. All right, when I plug in -3 here, I get a negative sign in that first parenthesis, but -3 squared is 9. 9 minus 2 is a positive number. So I'm going to get a negative times a positive, which is a negative. All right, I'm going to pick a number between -2 and negative square root of 2, like -1.5. All right, if I plug in -1.5, my first parenthesis is going to be a positive, and -1.5 times itself, Negative 1.5 squared is a 2 point something, and if I subtract 2 from that, I'm going to get a positive. So it's a positive times a positive, which is also a positive. Now, if I didn't know that, right, because I don't have a calculator, and so doing that in my head might be a little difficult, you can use these multiplicities to help you figure out what's going to happen, right? So if your function starts out negative, and at -2, you have a odd multiplicity, which means your graph crosses your x-axis at that point. Then if it crosses from being negative, well, you got to cross it and become positive, right? Then when I get to negative square root of 2, the multiplicity is also 1, which means my graph has to cross my x-axis again. So since it's positive here, it has to be negative there. And since the multiplicity here is also 1, then it has to cross again, and you have a positive there. So knowing the multiplicity of these things will also help you to determine fill in these number lines here. If you don't want to think about multiplicity, then choose some more numbers, right? So for instance, I can use 0 on that interval from negative square root of 2 to square root of 2. And when I plug it into this, that becomes a 2 times the -2, which is a -4, which is how we got the negative there. And then I can plug in a number like a positive 2 here. When I plug in a positive 2, that'll be 4, and that'll be a 2 there. 4 times 2 is 8, which is positive. Now, we want to see the intervals where it's less than 0, and we don't include these points where it equals 0 because this doesn't have an equal to symbol under our inequality. So my solution for less than is going to be this interval here and this interval here. So I can say that my solution set in interval notation would be from -infinity to -2, union negative square root of 2 to square root of 2. Okay? Just to go back to that bonus, I'm going to give you a little hint. This may actually be true, all right? So tell me why this multiplicity, tell me why this is incorrect, all right? Tell me why this multiplicity of this 0 here is actually 1. Tell me why the multiplicity of x cubed minus 1 actually equals 1. All right. Tell me why. And this concludes the video. And I'll request the actual bonus in class. Have a good day.